Good morning, all. Today's seminar topic is room temperature ferroelectricity in multiferroic gadolinium manganate. Its chemical formula is ZdMnO3. Today, this is my uh, research topic. What is multiferroics? As we know, multiferroics uh, is a phenomena where we can get both electric and magnetic order simultaneously coexist. Multiferroic materials nowadays they're very useful in memory devices because today's days miniaturization of the devices, how smaller devices we can make. So if we will find this multiferric property in a material, then in the same material add we can get both the properties of ferroelectricity and ferromagnetism. As we know, ferroelectricity is useful for processing data and ferromagnetism property is necessary to store data. So here we are able to find multiferroic behavior, that means both ferroelectric and ferromagnetic behavior in the same compound uh, of gadolinium manganate. And also we have seen the ferroelectric property is obtained at the room temperature, which is uh, very important for application purposes. But we will get the ferromagnetism, but we got the ferromagnetism uh, in very low temperature, which impedes the multiferric application. My topic of presentation is what is the aim of my work, and we will discuss some basic concept notes on ferroelectric multiferroic sorry and rare earth based manganites, which is a proven system for many emerging technology. Among the rare earth manganite system, we have chosen gadolinium manganite, which is a special material system in rare earth manganite. Why we select the material gadolinium manganite and what result we will get, then conclusion. Aim of my research work Aim of my research work is to prepare highly dense polycrystalline sample of multiferroic manganites, gadolinium manganites, by solid state reaction route and pyrophoric reaction route, which is a chemical route, using slow step sintering schedule in order to investigate dielectric ferroelectric multiferroic properties of the material for possible device application at room temperature. In brief, we will discuss what is dielectrics. As we know, in dielectrics are the material where electrostatic field can persist for long time, and these are the important dielectric properties: are dielectric constant, dielectric loss, power factor, conductivity, DC conductivity, and dielectrics mainly used in microelectronic industry, storage capacitors, non-volatile memory devices, magnetic tunnel junction devices, plasmonics, etc. So mainly dielectric behavior refers to variation of those properties, mainly dielectric constant and loss, with temperature and frequency, and also with respect to voltage and composition of the sample. Dielectrics are mainly two types: linear dielectric and non-linear. Linear dielectrics are those where dielectric material exhibit linear relationship between polarization and applied electric field. But in nonlinear dielectric behavior, we will get a switching polarization behavior, which we call the hysteresis behavior. So this is the non-electric dielectric. But in our sample, gadolinium manganate shows non-linear dielectric behavior. That means it shows ferroelectric behavior or hysteresis behavior. Multiferroic. What is multiferroic? It is a unique and novel property which has been discovered since a decade, where both ferroelectric and ferromagnetism can exist simultaneously. Ferro means material, electric means electric nature. The material where we will get, actually ferro means spontaneous behavior, spontaneous electric behavior if you will get, that is called ferroelectric. Ferromagnetic means spontaneous magnetic behavior if you will get, that is ferromagnetic. Spontaneous electric behavior means you will get spontaneous polarization or switching polarization in the material, and ferromagnetic material you will get spontaneous magnetization behavior in the material. And these two properties of ferroelectricity and ferromagnetism can exist simultaneously in a same material system, that we call the multiferroic. And this concept was introduced in the year 1994 by Schmidt. Uh, then after him, lots of research is going on. Mainly people are focusing on rare earth manganite system, though it is a proven system for many emerging technology. Its main property is it shows it has a perovskite structure, and it says having high spin polarization. All this property it is having. Why I have chosen gadolinium manganite for my research work? What is the intent basis of material selection of GTMNO3? It has multiferroic behavior already people have studied, uh, but people have studied multiferricity in this compound at very low temperature. What they got the result at low temperature, which restrict the application of this material at room temperature. Also, it is having high magnet spin moment around 7 by 2 among the 4F ion family in rare earth manganite system. And it is also having high Digeness factor among the rare earth ions. Also, it shows gigantic magnetocapacitance effect. Gigantic magnetocapacitance effect means the magnetic field can change the capacitance value. That means it shows high value of magnetization if you change the capacitance value of the compound system. Then these are the problems as I told in the previous slide. People have already got multiferroic behavior at low temperature around less than 50 K in a single crystalline sample, which impedes its application at room temperature. But no research work has been done in polycrystalline sample or as well as in thin film. So we have opted to do the sample preparation in polycrystalline form. This is the experimental procedure what I have adapted by solid state synthesis, solid state reaction route. First we have taken the sample of gadolinium oxide and manganese oxide, then we calcine at 600 degrees centigrade, then we prepare the pellets from the calcined powder. Then the pellet has been sintered from 800 degrees centigrade to 1350 degrees centigrade using slow step sintering schedule. Then we have done the XRD measurement, Raman, ferroelectric, PSCM, field emissions scanning electron microscope, EDAX, XPS, dielectric and magnetic measurement. So this method also I have followed in for some sample using chemical route, because I want to synthesize nano material in the nano form. So I have opted uh, pyrophoric technique route, and also we have achieved good result. Finally, we got the nanocrystalline product of GTMNO3. This is the slow step sintering schedule. What we have done by slowly we have sintered the sample up to 1350 degrees centigrade. So this is the furnace which indigenously designed by our laboratory. this is a electric furnace, and where we have calcined the sample at 800 degrees centigrade, and this is the another furnace which we have used to sinter the sample at high temperature, that means 1350 degree, and also we can go up to 1600 degrees centigrade through this furnace, vacuum furnace. And this is the apparatus, dielectric sample holder we have used. This also we have prepared by ourselves, by our team. And this is the accelerometer by which we can measure the dielectric measurement. And this is your ferroelectric loop tracer, where we have measured the ferroelectric behavior. This is the XRD measurement of my sample, which is centered at 800 degrees, 1350 degree, and also we have gone up to 1700. I am showing in the same slide for both. And in 800 degree sample, pure phase formation has not obtained because we have impurity peak around below 13 degrees centigrade. Then 1350 degrees centigrade sample is showing good crystallinity behavior and proper phase formation. But again, when we increase the sintered temperature, we got again the impurity phase of manganese oxide is came in the 1700 sintered sample. So due to limitation of the time, let us stop here. Final result I am showing. These are the density behavior. This is my EDAX measurement. This is the FESM picture of the sample of 800, then 1350, then 17. And as you are seeing, 1350 sample shows distributed grains, uniformly distributed grains with proper grain boundary, but it shows small pores, which small amount it shows in the microstructure. You will find small pores, maybe due to which we'll got the dielectric constant value, very good dielectric constant value. And this is my EDAX analysis, where I am seeing in my sample preparation I have got all the samples of GD, manganese and oxygen. Then this is frequency dependent dielectric properties. We have very dielectric constant with respect to frequency, then with respect to temperature. And you see in 1350 degrees centigrade we have observed dielectric anomaly around 110 degrees centigrade. And this is also, here I am showing the ferroelectric property. You see we have got a switching polarization, but there is some such switching polarization in all the three samples centered at 800, 1350 and 17. But we will get a very good result in 1350, where rectangular size loop we obtain having high saturation polarization. This is at a room temperature. We have measured all the ferroelectric property we measured at room temperature. Then this is the XPS study, where we are finding the valency state of the sample, and I am showing the magnetic behavior. And in magnetic property, as you are seeing, the sample shows the switching magnetization behavior, which is the ferromagnetism, only in 1350 degree sample, but in 800 and 1700 degree sintered sample it shows the paramagnetic behavior. Only 1350 sample is showing ferromagnetic behavior. So what we conclude, among all the sintered sample, only 1315 sintered sample showing good ferroelectric behavior around 373 K, and square type of novel hysteresis loop at room temperature, only in case of 1350 degree centigrade sample. So we can take this sample for our application purposes for room temperature application as a multifunctional material. Thank you.